Hi, in this video, we're going to talk about the derivative, but in the case that we have a function that is not real value function, but a complex value function or a vector valued function, which means that now we encounter the functions from closed interval AB to C, where C represents the complex plane, or functions whose domain is closed interval AB on the real line to and whose image is a subset of Rn, where Rn is the n-dimensional Euclidean space. And let's see how the definition for derivative changes based on this. So here the definition. If we have f that is complex value function, we say f is differentiable at a point x if this limit exists, where the limit is same, which is fy minus fx divided by y minus x. And of course, the derivative of f evaluated at x, if this exists, it is a complex number. And notice that before, when we were dealing with the real valued function, this is equivalent as saying that the limit of this expression minus f prime of x is equal to 0, right? But here it doesn't work. We cannot just write the difference of this and this. We have to evaluate the distance in terms of the norm in the complex plane, which is why we I highlight this absolute value sign. Because it doesn't make sense to talk about the distance between 2 points in the complex plane without indicating like which norm we use. So normally we use the norm that equipped in C, which is equivalent as the norm in R2. Okay, and then the first proposition, notice that we write the function, the complex value function usually in this way: f1x plus I times f2x, where f1 and f2 are real valued functions. Then we have f is differentiable at x if and only if f1 and f2 are both differentiable at x. And in particular, we can write the explicit derivative of f evaluated x in terms of f1 prime and f2 prime. And this is a proof. It is pretty straightforward. So the main idea is, of course, we want to show, given that f is differentiable at x, right? So this is a definition. At the end, we want to show f1, f2 are differentiable at x. So what you do is you rewrite in this way, right? Because both functions now are complex values, so you need this absolute value sign. And then what you do is recall the definition for f, which is equal to f1 plus I times f2. So just rewrite this using the definition of f. And we rearrange everything. So I put the real valued part here plus I times the real valued here. So you can see this term is in terms just using f1, and this is a term just using f2. And now we can see that the absolute value sign in the complex plane represents So I here highlight is the purple color, right? So when you're evaluating the magnitude of a complex number, it is equivalent as the real part square plus the complex part square, and then the root. So this is what we are doing at this step. So we just simply apply the norm in the complex plane. So we got this. And here we're using, I skip some steps, but it is clear that I use the sandwich rule. Why? Because this is always larger or equal than 0, and this is smaller or equal than this term. And the limit of this term is equal to 0. So we know this is larger or equal than 0 and smaller than equal to 0. Therefore, it must be 0. So similarly, we obtain this expression is equal to 0. And notice that I can write, I didn't write explicitly as I was. So this is same as saying, because f1 and f2 are real value functions, so we can, so the absolute value, the limit of the absolute value is equal to 0 implies the limit of the expression itself equals to 0. Therefore, we can get rid of the absolute value sign. And again, this because we can do this because f1, f2 are purely real value functions. Okay. And then now, if I continue to rearrange stuff, you will notice that this is exactly the definition of f1 of 2 are differentiable at x. So we're done, right? Okay. And then the next definition is about the derivative of the vector valued function. Here, m is larger or equal than 1. Of course, before we were focused on the case that m is equal to 1, but now m can be any natural number. And here the norm, I highlighted again, is Euclidean norm in Rm. So for example, m is equal to 3, then if I have a vector x in R3, then the norm of x is going to be equal to x1 squared plus x2 squared plus x3 squared, and then you take square root of that summation. Okay. So just keep in mind, we really need this norm to measure the difference between the two vector in Rm. And again, there is a similar proposition. So if we have f that is differentiable, if and only if each component-wise function is differentiable. So the f, recall that f is really like a vector functions. So f can be written as a vector of f1 dot dot fm, and then f is differential if and only if each of the coordinate function is differentiable. And you can try by yourself. So translate this problem into coordinate-wise and then apply what we learned in the first couple of videos. And then you're done. And then there's a theorem saying that f is differentiable at point x, then f is continuous. So we did prove the case that m is equal to 1 in the first video, I remember. And again, the proof strategy is going to be similar. So you translate this problem into component-wise, where each component is a real value function, and you apply the result about the real value function in your proof, and basically you're done. And then we have proved the real value function case already in lecture in video 1. Okay. And there are some operations that we introduce at the very beginning, and they are also apply in the case that we are dealing with complex value function or vector value function. So basically, if f and g is a function from ab to rm, and is differentiable, then the derivative of this is equal to f prime plus g prime. And for the product of two functions, so if you want to compute the derivative of product of two vector valued function, it is equal to, it's still you apply, still the product rule applies. However, you need to be extra careful because here you are multiply two vector value. Multiply two vector value. Therefore, it is the inner product rather than, it doesn't make sense to even talk about the regular product, right? Because we're dealing with the vectors. Okay, and to prove again, you can try to translate the problem into component wise, where each component is a real value. And you can apply the previous result on the real value function, and then you're done. Next, I want to discuss a little bit about, remember there are two important theorem, which is consequences of mean value theorem. The first one is L'Hopital's rule, and the second one is mean value theorem. Those are interesting and important theorems, and we wonder if they are still hold in the case that f is no longer a real value function. And the answer, unfortunately, is no. So it doesn't hold anymore. And then in this video, I want to show you some counterexamples. So consider example, complex value function, fx is equal to e to the power of ix. And now consider this interval, right? And then we know that f is continuous and on this closed interval and differentiable on the open interval. Therefore, if assume that mean value theorem is correct, then there exists x in this open interval such that this expression holds, right? Which implies this, which implies f prime of x equal to 0. So there exists x in open interval 0 to pi, such that f prime of x is equal to 0. However, if we indeed compute the derivative of f, we obtain this expression. The magnitude of this expression is equal to 1 because the magnitude of this expression is equal to the magnitude of I times the magnitude of e to the power of ix. And of course, the magnitude of I is equal to 1. And then the magnitude of e to the power of ix is equal to 1. If you are familiar with complex numbers, this so any complex number in this form is the complex number on the unit circle of the complex point. So this indeed has magnitude 1. You can also prove in this way. Therefore, we reach a contradiction. Why? Because by the mean value theorem, which we assume it is true, we obtain there exists a point such that the derivative of f at this point is 0. Meanwhile, we also know that every point on this interval, or every point actually in R, the derivative of f at every point has magnitude 1. So clearly there is a contradiction because how can 0 has magnitude 1, right? So therefore, the mean value theorem does not hold in this example. And in general, we cannot say at this point we cannot have a general conclusion for the complex value functions. Okay, what about L'Hopital's rule? Unfortunately, it does not hold anymore. And this is a counterexample. So consider two functions g and f, where F defined in this way and G defined in this way. And let's check. So we assume L'Hopital's rule applies, which means it holds, right, for this function. So we check the conditions, and we also notice that f limit of fx is equal to the 0 is equal to the limit of gx. So if L'Hopital's rule are correct, if L'Hopital's rule is correct, we should have the limit of this ratio is equal to the limit of the ratio of its derivative, and we can compute the derivative of the function fx and gx, which is here. And after some algebra, we got this expression. And since as x goes to 0, well, you might wonder this goes to infinity. However, there is I, and recall that every complex number that can be written in this way is on the unit circle of complex point. So what I'm going to say is the magnitude of this expression is equal to 1. So I'm going to change this. And moreover, as x converges to 0, 2x converges to 0, and this converges to infinity. So together, they converges to negative infinity. The whole expression here converges to negative infinity, and there is a minus sign. So 1 plus 1 minus minus infinity is basically positive infinity, right? So the whole thing becomes 0 as x converges to 0. Meanwhile, if we compute the ratio of this in a different method, which is more traditional, we write this and we divided x in both numerator and denominator, which is totally valid. So we obtain this. And as x, we know that this again is equal to 1. I'm sorry. So because as x converges to 0, this expression converges to 0. So this converges to 1, right? Therefore, if we use L'Hopital's rule, we see that this limit of the ratio converges to is equal to 0. But using the traditional method, which we know is absolutely correct, the limit of this ratio is equal to 1. Therefore, the L'Hopital's rule does not hold in this case, even though all the conditions of L'Hopital's rule are satisfied. Therefore, the L'Hopital's rule does not hold for vector value function. And you can also actually find some examples that it does not hold for complex value function. Therefore, we will not cover in this video about the mean value theorem or L'Hopital's rule, like the updated version of mean value theorem or L'Hopital's rule for complex value function or vector value function. We will not cover that. All I show here is that the traditional one that we introduced and approved for real valued version does not hold anymore for complex value or real value or vector value function. Okay, but there's still something hold. So if you recall the mean value theorem, which is basically what I wrote here, right? There is a following implication. So because f is because f is differentiable on the open interval AB, so how to so if we write this if we write this is smaller or equal than the supremum of f prime of y, where y is can be any value in the interval AB times b minus a. So this is not positive infinity. We think y. So we know that f is differentiable on AB. So f prime of y may not be continuous. Okay, so I think it is possible for this to be positive infinity. The inequality still holds, of course. I don't think that has to be bounded by. I don't think this has to be bounded by a real value function, a real value number, because all we know from the condition is f is continuous on closed interval AB and is differentiable on open interval AB. So we actually cannot say anything about its derivative is continuous or not. If f prime is continuous, then the continuous function on compact interval assumes maximum or minimum. So this may be upper bounded by real value function provided this is a complex interval. If we change this to be a compact interval, but anyway, I don't think that's intention for this implication. I think the implication does hold, even though f prime is not continuous, because it doesn't have to be, we don't have to make sure this is a real value, because the inequality still hold when this is infinity. Okay, and this implication is useful, and then I'm gonna show an example. So oftentimes in mathematics, inequalities are very important because we oftentimes, especially in we approximate things a lot, which means that we don't have the exact value, but we can at least obtain an upper bound. So this gives us an upper bound for sine function on the interval 0, 1. And then we want to show this is true. And we can use implication of Murray's theorem to show that. So sine function is continuous on the closed interval and is differentiable here, where x is any number between 0 and 1. Therefore, by mean value theorem, we obtain this equality, right? And because sine 0 is equal to 0, so sine x is equal to sine x minus sine 0, which is equal to sine prime of k, where k is any k is a value between the interval 0 and 1, times x minus 0, which is equal to this, and this is smaller or equal than this times x. So we're basically comparing this value among all the values in the interval 0 x, in the interval 0 and x. And notice that, so notice that the sine function, notice that the sine function is bounded about by 1. But I have a new problem. I have a new question because I feel like the derivative sine function, yes, it is derivative of sine function. So sine prime of k is equal to cosine k, right? And then cosine k, the supremum of cosine k, where k ranges over 0 to x, is upper bounded by 1, because cosine function can only take 1, -1 or 1. Okay, so this is equal to 1 times x, which is equal to x. Therefore, we have sine x is smaller equal than x. Okay, and so what I did is so we reviewed the mean value theorem for the real value function, and I introduced the implication. So we're still in the context of real value function. I just introduced this new implication, and I show that how this implication is useful. And so we have been in the context of real value function. And my point is, even though the mean value theorem does not hold anymore for complex valued function or vector value functions, this implication still holds for those two types of new functions. And we're going to show that. So let x is equal to a function, for example, it's a vector value function, which is continuous and differentiable. Then the claim is there exists a point x such that fb minus fa, of course, as I mentioned before, whenever you measure the distance in a space, right, you need to use a proper norm. So here the norm we're using is the Euclidean norm. And since we're in m-dimension Euclidean space, we're using Rm norm. Okay, and the claim is this inequality. Let's prove that. So let z is equal to fb minus fa, which is in Rm, and then we define a new function. So I'm going to highlight with pink because every time I see this trick, I'm going to highlight it. So we translate our problem into a new problem and focus on a different function. And then we want to prove some nice properties of the function, which is equivalent as our goal. So we define Vt is equal to z times ft, and where z is fb minus fa. So we have this. And Vt is a function from a to b to r. Notice that this is inner product. So the result, the image of phi, the function phi, is in real line. So the gist of this proof technique is that, okay, we are working with vector value functions, and we want to prove an implication of mean value theorem in the context of the vector value functions, right? But based on our previous discussion, we know that the mean value theorem does not hold anymore for vector value functions. Therefore, our intuition tells us we better not to apply mean value theorem directly on the vector value functions, right? So instead, we create a new function, which is scalar real value function, and we want to apply the mean value theorem on this function, which we know is correct. Okay, so let's do that. So there exists x such that this equality hold, and then we just plug in using the definition of Vt, which is equal to this. And then because this is an inner product, so we again apply the product rule that we proved at the beginning of this video. Okay. And z prime times ft, because z prime is fb minus fa, both of them are constant vector. Therefore, when you are derivative with respect to x, it is 0 vector. Therefore, this is a 0 vector. Therefore, we can simplify into this. Okay, and you can check my work by write down the steps by yourself. So basically, z inner product fp minus fa is equal to the Euclidean norm of FB minus FA squared. Okay, so we're almost there. Now we apply, we use definition for C, which is FB minus FA, and we have this expression. And then notice that this is still inner product, and we have a very famous inequality, which is Schwarz inequality, which states that inner product of two vectors is smaller equal than the norm, the product of the norm of each vector. So here we have the smaller equal than the Euclidean norm of FB minus FA times the Euclidean norm of F prime of X times B minus A. Okay, and this is exactly, so we canceled out this, right? We canceled one term of this, and so this one disappears. Therefore, we obtain this final conclusion. Therefore, we show that there exists X such that this inequality hold. And we finish our proof. So let's just write the outline what we have been discussed in this video. So we introduced complex value, so I'm gonna say derivative of complex valued or vector valued function, right? And then basic operations like plus, times, okay, and what else did we do? Show the traditional mean bias theorem or L'Hopital's does not apply for this type of functions. And then we show the weak, however, the weaker implication of mean bias theorem still apply. Okay, let me know if there's any mistakes or typos. Otherwise, I will see you in next video. Thank you.